Okay, let's start. So last time we, why is it blank? So can you, no, very weird. Share screen, share. Okay, so let's start. Maybe let's just, briefly recall basic definition of Brownian motion. So there are two definitions which are equivalent. So the first one is so we define right the Brownian motion is a stochastic process. It's a real world stochastic process. We usually write as BT. Some books it might write as WT or T or BT. This is our valid notations. So the first condition is, so if you choose like finite time, right? If you just pick a finite time slice, so T0, T1 to Tm, and so you can put the increment like BT0, BT1 minus BT0, right? The increment. So all the increments are independent and are called. So the center is 0, the mean is 0, and the variance is just the time increment. So if you just pick two time from T1 to T2, right? So this is so BT2 minus BT1 is Gaussian with mean 0 and variance T2 minus T1, and in different time intervals they are independent. Right, so this just tells the increment are Gaussian. And also the trajectory path, right? The trajectory almost surely is continuous. So this gives you a model of continuous type Brownian motion. Okay, so this one is not easy to establish, right? So if you need to spend some time on thinking about it, but our others are not that okay. Right. So you can think, right? So last time we mentioned, right, there are many ways to derive the Brownian motion, right? This is the way. The first we talk about Brachelier's work on Brownian motion. So it's very intuitive derivation. You can go through that. But of course, the easiest way to think about Brownian motion is the scaling limit of random walks. Just the standard, the simple random walk, right? Simple random walk. This is basically just the law central limit theory. Central limit theory. I want to point, right, is this. So to really derive the same limit towards the Brownian motion from the work, this is the scales you choose. This is scales you choose. So the delta t, right, in the discretization in time equals to delta x, the discretization in space squared. This is called hyperbolic scaling. Okay. So there are many properties, right? First, if you translate the Brownian motion, right, it's the same. It's called translation in time invariance. So BT minus B0, right? You just take BT minus B0. 0 is the initial state. So you can just get a new Brownian motion, which starting from 0, right? So this is equal in the distribution sense to the Brownian motion starting from 0. Okay, and this is basically just from our scaling, hyperbolic scaling there, right? Change the time t, change the time t, right? If you change the time s to st, so you just, it equals in distribution, you just put square root t out, right? This is basically from this fact, right? And also the independence, right? So this probably you see a lot, right? So if you do time scaling, where you change the units, this is Brownian motion, and if you change this, you just get 1 over square root of n bt. Later, in the stochastic differential equations, if you change the time variable, they say if you change time variable, this is d, this is e to right, the formula, right? For instance, if you write dxt, right, is a stochastic differential equation, then bt plus sigma txt dvt. So sometimes if you change the time, so this is integral term. If you change the time from t to t minus n, so then this is what we get in the integral form, right? This is also comes from the scaling fact, right? Come from the if you scale time by 1 over n, so it is the same as you multiply 1 over square root of n in front of dbt, right? Okay, just briefly recall what we did in last time. So let me just say a few words about how to show the existence of almost three continuous paths of Brownian motions. So we just read the book, probably don't understand well, but let me just say a few words. So how to construct Brownian motion, right, from dimensional distribution. So first, we should have a consistent family of finite dimensional distribution. We're starting from any finite time t1, t2, right? And we can define a finite dimensional distribution. So this is a finite dimensional distribution. It's just on Rn. This is a mirror on Rn, right? So let's compute the mirror on A1 times A2 times An. This is a Fourier set, or it's the basis for the Fourier set on all Rn. So this is just defined by the transition probability, right? The transition probability is given by the heat kernel, right? So this is the heat kernel or the density function of Gaussian process or normal process, a normal variable, right? Standard normal. Okay, from transition function, right? So this formula, right, this is exactly used to define the finite dimensional probability in Markov chain, right? It's the same, right? If from x0, right? It's like you from x0, and you compute you using the transition probability from x0 to x1, right? Then from x1 to x2, right? And you integrate all possible values for x1, x2, xn, right? So x1 is in A1, x2 is in A2, xn is in An. You just integrate all, right? So this is iterated integrals. Okay, so we can check, right? This mu n, this family of finite dimension distribution are consistent. So consistent means, right? If we so Rn, right, the distribution, the mirror we define in Rn is just the projection of the mirror we define on Rn plus 1. Right? So it's consistent. So once we have this, we can use the Kolmogorov extension theory. But if we just trivially use the Kolmogorov extension theory, we cannot get continuous paths. So what we really do, right? This is a theory we first stated, but this is almost useless. We not in practice we don't use this directly, right? So if we just use this, we don't have. If you just use this and this event, right? We just put all the event or continuous paths. So this is not measurable. So there's a homework problem related to this. So what we are doing is not directly use this Kolmogorov extension theory, get the existence of Brownian motion. So what we did is starting from something else. So we're starting from all the Q2. So Q2, right, is all the dyadic rationals. So it's all the rationals like 1/2, right? something like this. Right, it's all these this form of rationals, right? So all the rationals with the denominator given by two power, right? The power of n. So this rational, right? This dyadic rationals, right? If you take the closure, definitely you get the all the positive integer, right? So this is dense in the real numbers. So the idea is to do the following. Okay, so we have the same finite dimensional distributions, and we can define those finite dimensional distributions, but it's all the times given in Q2, right? All the times dyadic rationals. And we can show, okay, so we can show those paths, right? If you just restrict all the time in the dyadic rationals, so those paths actually are continuous, and not just continuous, actually are whole continuous as long as the exponent is less than 1/2, it's whole continuous. So if we have uniform continuity on any finite interval, right? And also Q2, right, these rational times are dense. So we can directly do the continuous extension from Q2 to all the real numbers, right? So this is what we do. Okay. Yeah, so this is a theory, another theory in the book. So we can assign probability measure. We can assign probability measure we knew on the path space from rational dyadic rationals to R, right? So all the paths with time given by dyadic rationals. So we can show by later the Kolmogorov continuity result to all the real numbers, right? So we first get a path, continuous path from Q to R. Then we do continuous extension to all omega from R to R plus to R. Okay, so the crucial part is to prove right, if we assume the Kolmogorov extension theory, so the crucial part is to prove the continuity, right? So the crucial part is just the following, right? This is what we leave here, right? Let's start here. So the crucial part is to establish continuity. Not just continuity, it is uniform continuity on any finite. So since by translation word, we can just consider uniform continuity from 0 to 1. Right? So once we have this, we can do the extension. Okay, we can do the extension. So all we need, so it's, I mean, all those work are by Kolmogorov. So maybe 1930s or 1940s, 1930 to 1940. So this is Kolmogorov is a famous result. So this result, the idea is the following. So we first, if we have an estimate in the form like this. So this is like, okay, we have we have a path, we have a stochastic process xt, t, let's say from, so here you can say from Q2, right? Or if it's R, that's fine. So you have the regularity in every sense, right? So this is the this is just difference all the time, right? This is kind of regularity in every sense. So this very famous result, this is not an easy result, right? A lot of results share this word. So this result says if you have regularity in average sense, so we can improve, we can get a pathwise regularity, right? So this doesn't, this is okay. You take average of the passes, and you take expectation, right? So they're not very far from each other, right? If T and S is very close, right? So then these two, then the path in average sense are not very, right? So But this is only continuity, right, in average sense. What we want to get is the following, right? We want to get with prime, so then that means almost for almost every trajectory, right? So for almost surely almost every trajectory omega, we can show the Holder continuity, right? So this is just the Holder continuity. Holder continuity. I just write here. So what is Holder continuity? So let's say we have a function f, right? We have a function f. Let's, for simplicity, assume this function defined from plus to r, right? So Holder continuity basically said, right? There's Holder continuity with exponent gamma. So if we say f is Holder continuous, if it's Holder continuous with exponent gamma, right? So this means for any x, there exists a constant c. So this c might depend on x, so such that so fy so fy minus fx, so is less than c. This c might depend on x, so x minus y gamma. This is called Holder continuous, right? You maybe you should be familiar with this, right? This is a basic regularity assumption for so Kolmogorov continuity result says the following, right? We have the moment bound, the regularity in average sense. You can get regularity. You can get password. So let's assume, right? Let's assume this result is true. Right? Let's assume this result is true. Okay. And we want to get some corollary, right? Some application. Okay. So let's assume this result is true, right? And this result can be extended a little bit, right? So let's say, so this x, right? So what we get, right? So is the continuity by two rationals, right? So if we know, so let's, I mean, if you have questions, you should ask. So let's a very easy corollary, as I said last time. So if we know almost surely xt is continuous, right? On 0 to infinity. So let's, if we assume almost every trajectory is continuous, and now, right, so this t, right, let's just say t is defined from 0 to 1, right? And you can extend this to from 0 to infinity, right, by a very easy argument. So let's assume if a priori we know xt is continuous from 0 to 1, right? So then, so Kolmogorov continuity result, right? So this result actually can be extended to all QR, not necessarily Q2, right? It's all Q2, right? This can be extended. So then QR can be just for any from 0 to 1, right? So as long as we know the trajectory is almost surely trajectory or typical trajectory are continuous, right? So this is just, you just extend, right? Just using extension, right? The continuous extension, right? That's almost trivial. Okay, so so now let's just use this result, right? So if we use this result, to the Brownian motion, right? So we can easily use this result for Brownian motion just by scaling. Right? So let's compute the 2m moments of the difference bt minus bs. Right? So by translation invariance, right, this equals to that, right? bt. So it's just bt bs is just b t minus s, right? And again, right, using the scaling relation, right? So here is minus s. We can take t minus out, but it becomes the square root of t minus s. So that's why we get t minus 2 power m, right? So then the remaining part is just the 2m moments of normal, standard normal distribution, right? So that's why we get the estimate like this, right? So for any integer m, right? So here is for any integer m, right? So we can use Kolmogorov extensions continuity result, right? But now m is 2m, beta is 2m, alpha is m minus 1, right? So we can choose any less than alpha over beta, so which is this, right? So as long as choose gamma, right? Since here m is arbitrarily large, can be chosen to be arbitrarily large. So as long as gamma is less than 1/2, right? So we can have the whole continuity for the Brownian path, for typical Brownian path. So we know, right, from this theory, the Brownian path, right, typical Brownian path is 1/2 minus epsilon holder continuous, right? So we can then just use this theory, right? Just use this theory and do the tension, right? So from dyadic, so this is the sigma field get by dyadic times. This is the sigma field by the dyadic by using Kolmogorov extension theory to finite dimensional distribution, but the time only chosen for dyadic channels, right? So we can do the closure for this and for this, right? So in the end, we get a path, right? So this is all the continuous paths, and this is a sigma field on generating by this continuous path. So later we use this to represent by the Brownian motion, right? So then we continuous Brownian motion, and this is the trajectory space, and this is a sigma field for this trajectory space. Okay. So yeah, it's probably a little bit confusing here. The idea is simple. We using Kolmogorov extension theory to generating distribution for paths, but all those times are dyadic rationals. So then we're using Kolmogorov extension, Kolmogorov continuity result to show those paths are holder, right? One holder by those results, those moments bound, those movement bound. So we can do the continuous extension to all the paths. So for all the paths, for the paths on the continuous times, right? So then we have the result. We obtain almost surely from time t bt, the Brownian motion is continuous. Okay. So for the remaining part, we want to show the very famous Kolmogorov continuity result, right? So this result. So this result is, I mean, maybe now it's not very surprising, right? So, but this is a very powerful result. I very believe the techniques in the proof is very useful. Maybe showing a lot of field, because this is a basic things. Okay, yeah. Now we just talk about the proof. So this is a Kolmogorov continuity result. Okay. So this result, so how to do that, right? So maybe I just go through the proof first. if you have time, you can go through the proof. But I have good exercise for you, right? For you to do practice. But there are some problems. So this part I won't talk about this part, the non-differentiability of Brownian motion. But there are some exercise. I will put this exercise in the homework. I will post an announcement later. This is a good exercise, and this is a really nice proof. And this proof can, so if you, so this proof is due to several due to three mathematicians, so-called this proof. So this is the theory 7.1.6. So differentiability of Brownian motion. So this basically says, so almost for typical trajectory of Brownian motion, they are not niches. So proof by this is by Dvorsky, Edosh, and Kakutani. But of course, the first proof is due to so Paley, Wiener, and Zygmunt. So Paley, Zygmunt, Wiener are all very famous guy, right? So Zygmunt probably worked in University of Chicago. Nowadays, there's a very famous lecture series in University of Chicago called Zygmunt, maybe Zygmunt analysis seminar. So yeah, I'm not very precise, but yeah. So those are very famous analysts. Okay, but not as famous as Kolmogorov, right? So let's just say, maybe don't say in very detailed way, but I want to tell you the idea, right? So why this theory works? Why this theory works? Okay, so what we want to do? We want to do, right? So first, going from moments bound, right? You average so in regulating average sense, we want to get almost surely we want to get almost surely convergence, regularity, right? We want to get almost surely regularity. So I can tell you, right? So this is just a continuity version of the Fourier-Cantelli lemma, right? So yeah, but let's go to the proof, right? So after that, maybe I can several comments. It's better, right, for you just to go this very carefully. Otherwise, you probably don't get a lot. You just listen to my proof, because you might feel it's artificial. But if you use this many times, you might feel this is the right way, right? Okay, so how to do that, right? Let's define a family of sets, right? So this is so here is all, we choose all the trajectories, and this is true. This is true. So what that says, right? This says so we want to capture all the omega. We want to capture all the omega such that so they are not too far, right? They are not too far from each other, right? So we do points, right? So they are not very far from each other, right? From this point to this point, right? So they're not very far, right? This upper bound for those increment. So GN says, right, on all those for we want to capture all the omega such that they're not very far from each other. If they move from I over 2n to I minus 1 to O n. So that means if you go for this small, those very small interval, right, like this. So you cannot change a lot, right? Cannot change a lot. So the idea later looks like the following. So if omega is in this set, right, from Kn to infinity Gn. So if you are infinite Gn, right, that means you have the finite, you only have very finite control of your growth for any scales of times. So then you have regularity, right? So the idea, right, as I said right here, right, is the following. If you have uniform boundedness, right, in different scales, but this boundedness will also be finer if you go to smaller and smaller scales, right? So if you have uniform boundedness in different scales, in the scales to decimal, then you can order continuity, right? This proof is not hard, but it can be harder if you want to get more delicate result. Okay, but the result is can be in the following way, right? So we just construct this N, right? N says, okay, in this scale, so all the paths does not too much, right? This is the oscillation. So the oscillation is in the order of this, right? In the scales of 1/2n, the oscillation of the paths in this order, okay? So if you, so the Gn just this behavior, right? The behavior in the scale of 1/2n. Okay, so here is the following just application of Chebyshev inequality, right? So this is a Chebyshev inequality. So we want to compare the GNC, right? So if omega, the mass is not at Gn, right? So how large it is, right? Large it is. It's just by so use GNC, right? This is GNC. GNC is the union of all those, right? The union I equals to 1 to n. So GNI, right? Take union, and there exists one segment that the counterpart opposite is just there exists one segment such that the oscillation is bigger, right? Is bigger. So we use the ratio of inequality, right? You can just do that. And for this part, right? So with this part, right? This is just 2n copies, right? I has 2n choices. And for this part, it's just using the Chebyshev inequality. And from here to here, you just using the estimate, the moment estimate, right? So using this estimate. Okay, for moment estimate. Okay, anyway, we can show this is small, right? So the opposite, so the complement of Gn is relatively small, right? So if you see this, probably you know, right? So if you sum up with n, it's finite. Right? So here, if you sum up with n, you get a finite number, right? So this basically says GNC actually can appear infinite often times, right? And if we just look at, as I said, right, if you just look at the scale in 1/10, right? So this scale is not enough, it's not good enough. So why, right? You cannot just get regularity from bonds, right? So because regularity is stronger, right? But we can really get regularity if we pass the scale to infinitesimal, right? We need all n, right? All n. We need all the assumption from n plus 1, n plus 2 to infinite, right? So we need all those, right? So this is the following lemma. This is done the following lemma. It says the following. Right? So if we choose the omega in Hn, choose the omega in Hn just captures, right? Just captures all Gn, right? Starting from to n, right? So if omega is in Hn means, so it means omega is, so for all n bigger than n. So that means we have the, so in each scale over, in each scale 2 over n, we have the oscillation is not large over than this number. So this is for n bigger than n, right? So as long as we have this, right, for any scales in 1 over 2n, so the oscillation for path in that scale is not larger than over 2n to gamma. So we actually have the regularity, right? We actually have the Holder regularity. So this is the, right? So that's the conclusion. This is the conclusion. Okay, for any Q and R which is small, right? As long as Q and R is small enough, we have the Holder regularity. Okay. So this is not very hard to prove, right? But let's just tells you how to prove that, right? So let's with this assumption, right? Q and R are this close, right? This close. So we can write so Q and R this close. So there is this is smallest number of K such that Q and R are in the interval IIK. Right? So IIK is given by this form. Right? So this makes sense, right? Since Q and R are this close, right? So here there's an integer, there's a rational of this, right? And so there exists smallest m such that let's say Q is here, R is here, right? So we can represent Q and R in the following way. This is the first number, they are the same. So then, since R is in the right, you add up several numbers, right? You add up several numbers. Okay. Yeah, you add up several numbers from here, right? You just add up several small numbers as well. You minus several numbers. So then, right? Then just compute. We can just estimate x cubed minus x, right? So as I said, right, so there's a typo in the, I mean, there are many typos of fifth edition, but in particular here, m can be small, right? So m is not bigger than or equal to n, right? So this is wrong, right? This is wrong, but it doesn't the of this. Okay, so let's just right. In the end, we can show this we can ask this, right? So then, right, we just to try quality for many times, right? So this is our Q, and we know Q equals to X. Q equals have a representation this Q minus 1 to Q1. Q1 now is the integer is bigger than n, right? So something, so Q this is K, right? So but Q1 to QK are all bigger than n, or n, yeah, all bigger than n. So we can estimate the distance between XQ and XI over 2n. So you can do this, it's just a computation, it's just computation. And in assumption, this omega, this trajectory path, this trajectory is chosen from Gn, from Gn for any n is bigger than capital N. Right? So we can do all the summation, This is just using a relaxed bound. And in the end, we know, so this Q0 so actually is bigger than QR. Okay. So then we get this bound, right? So y2 minus n0 is less than q minus 2, right? It's because, right? So here, this is I over 2m, right? here is Q, right? Here is Q, here is R, right? So this distance definitely is bigger than this, right? Bigger than this, right? So this is a true estimate, but this Q0 is not M, right? So that's the typo in the textbook. So N0 is new number. So new number chosen is the smallest number in Q1 to QK. So this N0. So here N0 is the minimum of Q1, QK. This is big N, right? This is bigger than. So we have and this Q0 is less than Q minus R. Right? So we use this observation. Similarly, we can do the same to measure the distance between AR and XI over 2N. Right? So this is how we get the main estimate. Okay. So if we sum up, right? What do we get, right? We get, we said in the beginning, right? So if a trajectory path, if a trajectory is chosen, right, in all Gn, n is bigger than, for n is bigger than capital N, right? So that means in different scales, the oscillation is no bigger than this. Then we have regularity. Then we have Holder regularity for all QR, which are small, which are close like this, close like this. Okay, so this is a lemma. So actually, this lemma almost complete the proof, right? But we need to sum up. So let's just sum up. Go back to the proof of Morph theory. Okay, this is our previous definition. GS says in the time scale in the 1/2n, the oscillation is less than 2n over gamma. Right? And we can estimate the counterpart, the complement GNC, right, by Chebyshev inequality, right, is like this. Right? So we can estimate all the counterpart, all the complement of HNC, right? So of HN, right? So this HN complement can be estimated by this number, right? This is basically just by computation, right? Just to sum up all these things, okay? So by Fourier-Candeli, right? Since this, of course, is finite, right? This is finite. So by first Fourier-Candeli, so we can show so infinite often. So if omega appear infinite often in Hn, so it has probability 0, right? So has probability 0. So this Hn complement is 0, right? So is 0 mean following. So this, the probability of HNC infinite often equals 0 means almost surely omega for typical trajectory, there exists a capital N such that as long omega in Hn. So such that omega is just in Hn, right? Because HNC cannot appear infinite often, it's almost surely, right? So that appears, right? That stops appearing HNC when N is enough, right? So as long as N is large enough, omega is Hn, right? So this just tells you that, right? It just tells you that. So which tells you, right, as long as Q minus R are small enough using the lemma, right? So this is actually the 2 minus N omega, right? So as long as Q and R are small enough, we have the regularity, right? So for fixed omega, this is fixed, right? This is fixed. So we can just choose a path for Q there, R there. We can just choose a path, S1, S2, Sn minus 1, in Q and R, and which just need to change a bit, right? So we get a whole unity, but with maybe a larger A, right? Okay. But this is fine, right? This is fine. This actually already prove Kolmogorov theory. Kolmogorov theory. Okay, so let's just go back to the theory. Just to say it again, right? Okay, so this is a theory, right? I can tell you, right? This series, you want to do study regularity of some solutions, right? PDE, OD. This is a basic tool, but of course nowadays there are more advanced tools. But this is the basic tools. I mean, or the proof, right? The proof is gives you the basic tools. If you want to establish continuity, like hold a continuity, or lose continuity, or anything else, so usually it's easy to have those type of estimate, right? You have average sense, or you have some integral type bond, right? This is easy to have, and then you want to extend this to a pathwise estimate. This is not easy to do, but one thought is okay. So if we have the result, if we have the boundedness, right? If we can do the different cells boundedness, right? Probably we can extend. We can get the regularity. Yeah. That's what what the proof here, right? So this is the idea right here, right? We have uniform boundedness in different space scales, right? So you can have so here space means time, right? It means 1D, right? So so you can have holder continuity. Okay. So it's like, oh, right, so we use since here it's almost truly equivalence, we use the Brownian Lee, right, as well. Okay, I will just finish this section, right? So for the proof of non-differentiability, I won't talk about that, but I can tell you, so this is a very elegant proof. The problem, this probably this is also related. You need to read this in order to do the exercise, right? Basically, it's the same. It's just modify the parameter, like k here, k there. So here there's a parameter 3, right? And there's also k, right? There's also a parameter k here. You modify this parameter 3 and this parameter k. You can prove almost surely Brownian paths are not holder continuous for any holder constant, for any holder exponent bigger than 1/2, right? So almost surely Brownian path is not holder continuous if gamma is bigger than 1/2. So this is a theory you can prove. You mimicking the proof here, Okay, so so that's all for the Brownian, the first section. So if you have questions, you can ask. Yeah. Okay. Okay. So if no questions, I move to the next next section. So this section, I will probably do a little bit fast because so it's relatively easier compared to the previous one. Maybe it's bound to do fast. So so I want to finish this section, the next section, strong Markov property, but that without proof, right? So again, right? So here I will just state the Markov property, and with many corollaries, but I won't prove this. So probably we will finish Markov today. Not today, today and on Wednesday, but since we are only will stay then on strong Markov property, maybe a little bit by past section 4. So then, so the next for next the last week, we talk a little bit about martingale, but that might be quick, and basic Ito formula, Ito's integral. So we probably 2 lectures there. Okay, I won't do full details because most of the part you can read by yourself. Okay, so yeah, let's start. So so we want to study, we want to study the Markov property of Brownian motion, right? Of motion. So here, right? So intuitively, this is easier, right? By independence, we know, right? So this actually really have Markov property, right? Because if you look at, right, for instance, if you look at BT minus S minus BS, right? So this is a Brownian, this is a normal distribution, right? This normal distribution doesn't depend on BS, right? Or that depend on everything happens before BS, right? But we need to make this precise, right, in mathematical way. So what does this mean, right? Right. So this new process, right? This is a Brownian process, the Brownian motion. This is a Brownian motion. This is a new Brownian motion, which is independent of what happened before S. Right? We know this, right, intuitively, but what does this mean by the what happened before S, right? Which is the information before time S. The information of what happened before time S, right? So a very natural idea, okay, we just choose all the Brownian slides, right, BR, right, for all R less than S, right? So we call this Fs naught, we should call Fs 0, not. So this is all the information we know up to time S, right? This is time S. We choose all the information we know, right, up to time S 0. So we call this Fs0, right? Basically, this is just the information we need, right? So to make this more rigorous, right? We first replace this very natural choice Fs0 by a slightly different one. But let's see, this slightly different one is actually just equals to Fs naught. Surely. So this sigma field and this sigma field actually are more or less the same, right? But so if we start from Fs Fs positive, right? This is easy to establish some fact, right? So for instance, Fs plus. So this is easily to check if it continues. So what we mean by rate continuous is the following. If you take all the time, which is bigger than t, right? So we take the union of the intersection. We take the we take the intersection. So it's just according to the definition, we can check this is exactly ft0. This is wrong. This is wrong. This is sorry. This is so this is a right continuity, right continuous, which is easily, right? So we can just check this by one line. But to say right continuity for Fs0 is not easy to say, right? Yeah. But later we will see by some discussion, we will see these two sigma fields are basically the same. Right? So yeah. Okay. So you can think this if what you can think, right? So Fs Fs plus, Fs plus is kind of some right limit, it's kind of defined by right limit, right? So this is called, so in the textbook is called allows us an infinitesimal p under the future. So this actually, right, right, if A is between, so let's say T, if A is in this sigma field, right, so means, so A is in F T plus epsilon naught. So for each epsilon bigger than 0, right? So it's called A if A is in FT plus, so actually A is in any sigma field F naught for any bigger time, right? For any infinitesimal bigger time, right? Okay. Later we will show these two are basically the same because the Brownian path actually almost surely continues, right? You probably can find a lot of weird effect. So there are many different behavior. So in Brownian motion, right? So you compare Brownian motion to some discrete analog. There are many different things. Right? So you see several later. Okay. So this is just a basic setting, right? So px. So px is the probability measure, right? Charge continuous path space, and this is the field generating by the coordinate map, right? By the path, it's continuous, and we assume the Brownian motion starting from x. Is starting from x, so we have a probability measure px, and as what we did in the Markov chain, so we can define shift, right? So what does this shift means, right? Shift means the following, right? So if we shift s, right? So this is a Brownian motion. Let's say this is a Brownian motion. So we shift s, right? Then basically we just cut this part, and we just look at all the behavior starting from time s, right? From time s, it's cut off the part of the path, right? Cut off the part of the path for time s, right? And then the time s, right? The previous time becomes the initial time, right? Becomes the initial time. Okay. So what is the Markov property, right? So Markov property is the following, right? The statement is exactly the same as we did in the Markov chain, right? So, but the only thing different is now this. So this is a new sigma field we used, right? So this is not Fs naught, right? It's Fs plus. And so this is shift as well, right? This is a bounded measurable function. It's bounded measurable function. So if we do shift theta s and evaluate and take the conditional expectation with respect to Fs, right? We get just so this is the Ex, not x, or let's using y. Let's using z, y. So if we just look at the EZY, this is a number, right? But if we vary z, right, this is a random variable. And what the right hand means here, right, just first compute this and evaluate the value and BS. So BS is just BS, right? Is the Brownian motion and time s. So of course, right, easily, right, by Markov property, which you can find proof in the textbook. So we can see this is as not measurable, Fs0 measurable. So by the conditional expectation, right, this is Fs plus measurable. So So this is a random variable we project to the sigma field as a plus. So we get a random variable which f as plus variable. This is f as 0 variable according to the copy. So you show fs plus and fs 0 are basically the same. You can find the book again, right? You use long-term class theory. We choose some special functions, and we can the conditions to find a very special family of fy first. So, for instance, we can choose a function like it's generated by a family and by a family of so this fs this y only acts on the time tm. Yeah, so this is actually btm, right? Btm. So this fm only on the time style of Brownian motion and tm, right? So we can establish the property for this type of y, and then we can use in modern time theory to extend this result for just bounded numerable function. About proof, right? There's a whole page on the proof. Probably it's not good to talk about proof here. Okay, so let's continue our discussion of the sigma field fs0 and fs plus, right? So from the Markov property, as I said, right, so this is fs0 variable. This is fs0 variable. Okay. And you can see fs0 is definitely smaller than fs plus. So because fs plus, so it contains more. This is so how to say, so fs0, so actually contains in fs0, right? And fs plus is just the intersection of all those for h equal to 0. Okay? fs0 is definitely smaller than fs plus, right? Then we put plus. So we can do the projection, do the conditional expectation of this one, right? With respect to f0, right? Since fs0 is smaller, right? fs0 is smaller, we can just ignore this and get that, right? So it's best property of conditional expectation. So using previous Markov property, right? So we can get two are equal, and in particular, these two are equal. Okay. So what does this tell us, right? This tells us for any functions, right? If you do the shift, then the two sigma field, they are the same, right? They are the same. Okay. So it maybe probably don't look good, but everything like I probably should back. Yeah, this way probably looks right. Okay. So right, this is the basic observation, and we can extend this observation to a genus of families. Here, right, use the similar techniques to extend to get this theory. So this theory says for general bounded function, which is C variable, so this just means variable. For a general variable function, is like with respect to the sigma generated by coordinates. So this says if we condition on the sigma plus, right, fs plus, and condition on sigma 0, right, they're the same. So this is like a generalization of the previous one, okay, of the previous discussion. So how to do that, right? It's relatively easier. So we just check for this a very particular choice of bounded variable function. We choose this very particular bounded variable function. So we can write this z is just a multiplication of several several functions. Fm is bounded, and this is just our previous special choice of y, the proof of Markov property. Right? So you can regroup this time T1, T2 to Tm, right? And you choose all the paths which is less than s. You choose all the part which are less than s, and write this as a variable x, right? So for all the time which is bigger than s, you can do the shift, right? You can do the shift. Okay, so we can write this z as x times y composed with shift, right? So using previous discussion, right, if we do the projection to fs naught, right, we can by the representation of z, right, which is x times f composed with shift, right? So since x, of course, is fs plus variable, so we can put x out. So then we just compute the conditional expectation of y composed with shift. Right? By Markov property, Markov property. So the conditional expectation is really this, right? It's really this, which is f0, fs0 variable. X is also fs0 variable, so the product is also fs0 variable, right? So which tells us this, right? Since this is since this is S0 variable, right? So this should equal to the projection to S0, right? Right. So right, the same discussion as here, right? As here. Okay. So by this theory, so we can say, right? So we can say FSO and FS plus are basically the same, right? So this is a discussion, right? So in the previous theory, we have this. Right? You do the projection fs naught, right? Equals to the equal project to fs0. So now if we choose z, right? You choose okay. First, right? If z is fs0 variable, of course, z is fs plus variable, right? Secondly, right, if z is fs plus variable, right, so then by the previous theory, right, we know this equals z, right, and also it equals to projection to fs0. This means this is z. Right? So of course, right, z is f0 variable, right? So that means reverse direction is all true. So what does this mean, right? So for any bounded function, you cannot really distinguish S0 and Fs plus, right? So this means, so S0 equals to Fs plus almost surely. So which means are the same up to a null set. So null set means probability is zero. The probability, if it's variable, it has probability zero, or it's a subset of a probability zero. It's a subset of probability zero set. So Fs0 and Fs plus are the same. You can just think they are the same. The two way of definition of current information, F0 and Fs is the same. Okay. So the previous all up to now is just a discussion. We haven't seen anything interesting yet. But you see that now, so the first color is Brownian's 0-1 law. So what was I mean, it's called 0-1 law, but really the germ field is trivial. So there are two, right? If you look at the zero time, F0, F0, and F0 plus, right? So of course, this should be equal, right? This should be equal almost surely, right? I know this is trivial. So this should be trivial as well. This should be trivial as well. And this tells us the Blue-Mansell 0-1 law. I mean, this looks like very naive observation, but sometimes it's very useful. Right? If we want to study some in time, right? Yeah, you see that. Okay, the proof is almost trivial. I don't want to say the proof, right? Proof is just repeating what we did for the previous theory. So it basically says if A is in the germ field, right? Germ field is the microscopic, right? It's a micro or infinitesimal field, right? And times 0. So if A is trivial sigma field, right? So if A is in the germ field, F0 plus, then so it either has probability 0 or has probability 1, right? So this is a theory. I mean, basically says F0 plus is trivial, right? Proof is exactly the same before, right? So it's just 2 lines. I won't prove this, but I want to give you application for that. Okay, so that's said, right? So using the Markov property and basic observation before, like Blue-Mansell 0, for instance, we can study the local behavior and the time behavior of Brownian motion. So local behavior of Brownian motion, local behavior. Okay, so let's see first, right? So let's see first. Okay, so we define a stopping time. This is tau. Tau is a stopping time. It's the continuous type stopping time. We haven't defined it yet. So the stop time is first for continuous Brownian, continuous stochastic process. Actually, is in next lecture, right? In next section. I can tell you, right? Tau here is the stopping time. So tau is the heating time. Tau is the heating time of positive for the positive axis, right? Positive axis. I mean, you can guess, right? So this tau should be 0, right? So this tau is the first time the Brownian motion hit the axis, right? So let's say starting from 0, right? If starting from 0, of course, this should be, I mean, this tau should be 0, right? So tau cannot be bigger than 0 because, right, so for any tiny time, it can be positive, right? Now, if you think BT emotion as a scaling limit of random work, right? So this tau can only be 0. But we want to prove this, right? So the previous discussion can give us a very easy to give the proof, right? So how to do that, right? So let's a priori choose a time t. Choose a time t. So if the heating time is less than t, right, is less than or equal to t, that means it should be bigger than that. So why? So okay. So if BT is bigger, right? So BT probably not the first heating, but the first heating should at least be smaller than t, right? Can be larger than t. So if t is bigger than 0, then the stopping time or the heating time should be less than t. So of course this is true, right? This is trivially true by definition. But we know BT is a Brownian motion, right? Which so BT satisfy is a normal distribution, right? With mean 0 and variance t, right? So BT bigger than 0, of course, has 1/2 probability, right? So this is just symmetry of normal distribution, and this is true for any t. So this observation is true for any t bigger than 0. Okay, so we can say t goes to 0. If we set t 0, so it becomes smaller and smaller. this becomes smaller and smaller, but is strictly decreasing. So this limit works, or this limit works, and this limit should be bigger than 1/2, right? So, but tau equals to 0, right, is in the trivial, right? So tau equals to 0 should only depends on this, right? Tau equals to 0 should in the germ field, right? So this is called germ field, sigma field. So by Bloom-0, 1 law, right? So this can only be 1, right? Because the probability can either be 0 or 1, right? So now it's bigger than 1/2, so it should be 1. So at the end we have, right, almost the tau, the heating time to the positive axis is 0, almost surely, right? So this makes sense, right? Because if you think motion as a scaling limit of random walk, right? So in very tiny time, you can visit the positive axis, right? Okay, so this is visiting positive axis. So we can also, right, starting from 0, right, it must also hit the negative part immediately, right? So immediately. So this theory tells you the Brownian motion positive part immediately, and also by symmetry, it must the negative part immediately, right? And also we know the Brownian path, typical Brownian path is continuous, right? So this T0, right, you visit 0, the point 0 also immediately, right? So if you visit the positive part immediately, you also visit the minus part immediately and path is continuous. You must cross 0, right? And sometime, right? So T0 actually also equals to 0 almost surely. Okay. Yeah, this is Bloom-Menzel's 0-1 law and application. So this is the behavior and time 0, right? If you send t equals to 0, there's some weird behavior. So you must be very careful when you send t equals to 0. I mean, if you want to use some boundary condition, right? If you want to solve some value, right, using boundary, you must be very careful, right? As you might boundary condition. So maybe you just say a little bit about maybe two more minutes about long time behavior. We will go back to this next time. Yeah, maybe we just go to this time. I can stop here, answer your question. But this series behavior is actually the 0 time behavior. You send t equals to 0 by observing the following observation. So if you have BT is a Brownian motion, you do the following transformation, right? So x0 equals to 0, and also the shift, we do t times b1/t. So then this actually also defines a Brownian motion from 0, okay? It's very easy to check, right? But actually the most difficult part is to show xt really goes to 0 as t goes to 0. But this can be shown by strong law of large number. So by this observation, right, we do the time reverse, right? Not reverse, you take the reciprocal, right? 1/t and do some do multiplication, right? You'll be define xt. So actually xt, you can, in distribution sense, it equals to bt, right? So to study the long time behavior of bt, right, is kind of to study the local behavior as t goes to 0, right? So by this observation, okay. We will start from here, maybe next time. We'll start from here, maybe start from here next time. Yeah, we start from here next time. And probably we will finish the strong law, no, strong Markov property next time. I will just stand. So with some definition or story time, so it will be quick. If you have time, it's better if you prepare, you read a little bit before the class, right? Or you can review it after the class. Yeah, any questions? Okay, if no, yeah, maybe unmute all. Right? We want to ask you. Yeah, I should right. So because some people are talking all the time. Okay, yeah, I will stop recording.